announcement that I forgot to say in the morning, which is after the talks, we can use the building where we were having the coffee break. In particular, the floor above the coffee break has many rooms that you can work and discuss. There is an auditorium at the end. There are very nice sofas, one floor up. There is a rooftop, which is nice for discussions and places outside. And in the -1, there is another auditorium. So we can use any place in that building, which is great for informal discussions until 7 p.m. And the conference dinner is tomorrow. And that's it. And the schedule, there was some small edits in the schedule. So tomorrow, after lunch, we will start at 1:45. But it should be in the schedule online. Very good. So it's a pleasure to have Joe tell us about Hagedorn and integrability.
All right. Well, let me start by thanking the organizers for inviting me to give this talk. One thing Pedro did not mention this morning is that this is the 20th anniversary of IGSD, and it's good to see that still we get a lot of people coming to these conferences. So it's quite exciting for me. So anyways, I want to talk today about some work done last year and ongoing work this year with my fabulous young associates, Simon Eckhammer and Charles Tull. And I want to talk about the Hagedorn temperature and how we get this from integrability. But I'm sort of trained as a string theorist, so I'll basically start this talk by talking about the Hagedorn temperature and string theory. And then I'll move on to how you can, how putting it in curved space can change things. And then I'll talk about our results from using the quantum spectral curve. I won't say too much about the quantum spectral curve because, as Carlo said last week, using a whiteboard, one should not talk about the QSC. But anyway, Simon gave you a very beautiful presentation this morning, so you can have some idea of how things might have worked in that case. Okay, so let me start by talking about thermodynamics for string theory. So in string theory, when you heat up a gas of strings, it turns out that the partition function is actually dominated by long strings, not actually short strings, but by having one long string as opposed to having a bunch of short strings. And the reason for that is because the entropy for long strings basically grows quite rapidly. We know that for string theory, that the energy of a string, so I'll call this E, is basically equal to the length of the string divided by the tension. So sometimes I'll call this 2 pi alpha prime, but sometimes I'll write this as L over 2 pi times the string length squared. Okay, and so the partition function then for a single string, I'll call this Z1 as a function of T, okay, that this should be proportional to, say, an integral over the length of the strings times some density, which depends on its length, times e to the minus beta times the energy of that string, which is L over 2 pi ls squared. Okay, and so now the question is to figure out what this density is here. So this density, dlnl, I can write this in terms of, say, in terms of the energy, so dE of, say, rho of E. Okay, and this is basically equal to dE divided times 1 over E times e to the minus d over 2, which is the number of dimensions it's living in, times e to the minus beta times the energy. Sorry, not that. Times the energy times some constant I'll call beta h. Okay, so let me sort of explain where each of these factors come from. So you can sort of think of a string as being like a random walk. Okay, but it's not quite a random walk. For one thing, the string is closed, so it comes back to itself. Okay, so it's like a random walk, but we should sort of divide out by the volume that the string occupies in space, okay, in order to force it to come back to itself. And that sort of accounts for this factor here. Also, the beginning of the random walk is arbitrary. Okay, so we should divide out by basically the length of the string, which accounts for this factor here. And then finally, it's like a random walk, and the longer a string is, basically each length of the string adds, basically, it sort of increases exponentially in its length. So we basically have this exponential factor multiplied by some constant times beta h. Okay, so that would be our partition function. And so then, so if I then, I can rewrite this whole thing then, my partition function z1 of t, or beta, okay, is this integral dE over E times e to the, let me write it like this, as an integral of ddk over 2 pi to the d times e to the minus epsilon times e times some factor ls cubed k squared, okay, minus beta h plus beta, okay? Where I basically replaced this e to the minus d over 2 by this integral here, okay? And now I can do this integral over epsilon, over e, okay? And that's basically just going to give me this log factor. It's going to give me, this will be equal to minus 2 over 2 times the trace of a log times minus del squared plus 1 over ls cubed times beta minus beta h. Okay, so what's going on? Okay, well, this is basically the free energy. And you can see I wrote this as 2 over 2. And so basically what's happening is that as beta approaches this constant beta h, okay, I end up with a massless field here. And this would be the contribution of a massless, of a complex scalar with this mass term here, okay? So basically what you see is that you have a complex scalar, okay, with a mass, with its mass squared, is equal to 1 over ls cubed times beta minus beta h. Okay, so when this scalar becomes massless, okay, then you can see that the partition function will blow up, okay, and it's at this particular temperature that it blows up, and this temperature is called the Hagedorn temperature. So the Hagedorn temperature is equal to 1 over this beta h. Okay, so it's basically telling you that the thermodynamics of that string theory should be undergoing some phase transition at that point. Okay, and that's our Hagedorn temperature. Okay, so that's my review of the Hagedorn temperature. So anyways, this complex scalar is sometimes called a thermal scalar. And we can think of it, it's basically, it's a winding state with winding plus or minus 1 around a thermal circle. We'll call this tau, which is identified with tau plus tau beta. Okay? All right, so let's start with string theory. Let's start with type 2 string theory. Okay, so in type 2 string theory, basically we want to compactify, say, the time direction. We want to make it Euclidean. And so we know how to compute the mass squared for that. The mass squared should be equal to the radius divided by the tension, the radius squared, 2 pi, this tension, this is squared. Okay, and since we turned on a temperature around this thermal direction, we've basically, we have to break supersymmetry, and we basically have to twist such that the fermions pick up a sign. Okay, so that's going to end up giving us a 0-point contribution, and that 0-point contribution is 2 over alpha prime. Okay, and so then when this will be equal to 0, you can see then that beta h, okay, that beta h will be 8 pi squared over alpha prime, which if we write in terms of, if we use the ADS-CFT dictionary, if we're talking about n equals 4, this is square root of 8 pi squared over lambda to the 4th. Okay, so we know then that for n equals 4, the Hagedorn temperature, which is the inverse of this, will scale as lambda to the 1/4, okay, in those sorts of states. Okay, so this is the Hagedorn temperature in flat space. Now let me tell you what it is. Let me start explaining it in curved space. So I'm basically going to consider the case where I have ADS in d+1 dimensions, because not only can we apply this to n equals 4, but we can also apply it to ABJM theory. Okay, and here our metric will be equal to 1 plus. I'll use global coordinates of d tau squared plus dr squared over 1 plus r squared plus r squared times a d minus 1 sphere. Okay, and so what I want to do is I want to find a correction to my Hagedorn temperature that I'll get by putting this on a curved space. So this is in flat space. Now I want to consider the case on curved space. And this was actually done by Maldacena and I forgot his name already, sorry. Maldacena and Urbach, sorry. Maldacena and Urbach in 2022, I believe. Okay, and so the idea is the following. So let's suppose I have a winding string. So now I'm going to consider thermal ADS. So when I consider thermal ADS, I'll make this Euclidean. Okay, and I want to consider then I have a very light winding string, so I'm going to be very close to my my critical radius where the thing will become massless. And so since this is a very light state, I can basically just think about supergravity. Okay, so I would have then, in this case, I'd have an integral times some metric factor times, basically, I have chi bar times chi, where this is my complex scalar, and I have some mass term. This should be a minus. A mass squared term times chi bar chi. And my mass squared, now, since I'm now on this curved space, my mass will actually have some dependence on the radius. Okay, so my mass squared r, okay, will be equal to basically this beta over 2 pi alpha prime squared times, since this has some r dependence here, times a 1 plus r squared, minus some 0-point contribution that you get from the string worldsheet. So let me call this C. And C is equal to, let me just write it in terms of that, is equal to 2 alpha prime plus some correction delta C. Okay, and the correction, I'm going to need a correction because I'm going to be on this curved space. Okay, so, but for now, basically, I can sort of forget about this term and just worry about this term, so the lowest order correction. And what I find then is that if I solve for this, basically I'm going to have the following equation. I'm going to have 1 over r to the d minus 1 times dr of chi, dr of r to the d minus 1 times 1 plus r squared, dr of chi with a minus, and let me put a half in front of it. Then plus a half times beta over 2 pi alpha prime squared, r squared times chi of r is equal to a half times this correction 2 over alpha prime. And then from this part over here, I'm also going to get a beta over 2 pi alpha prime squared, like that. Okay, so what I'm doing is I'm assuming that my chi that I'm solving for basically only has r dependence. Okay, so I'm looking for some profile where I have this chi that's only an r dependence. Okay, so to a lowest approximation, okay, I can basically ignore this term. So let me ignore that term. Okay, and then what I'm left with is basically the same equation that you'd find for a harmonic oscillator in d dimensions. Okay, so this is actually the radial harmonic oscillator in d dimensions. So if I just match terms, you can see that the omega for this term is basically just beta over 2 pi alpha prime. Okay, because that's this term here. This term here is then the energy of the harmonic oscillator, and this then would be equal to, so the energy of my harmonic oscillator, let's call it E, is equal to half times that term, beta over 2 pi alpha prime squared. Okay, and since this is a radial d-dimensional harmonic oscillator, we're going to want our chi to be well behaved out at infinity, which means that it has to fall off exponentially. So it's basically it's like quantizing this harmonic oscillator. So this turns out to be equal to d over 2 times this omega. Okay, so you solve. So now this is omega squared. You solve for this in terms of this beta. And to leading order, then what you find is that, let me write it in terms of the Hagedorn temperature, that the Hagedorn temperature, TH, okay, is equal to basically 1 over this term here, 1 over this, 1 over the square root of 8 pi squared alpha prime, okay, plus a term that's basically d over 8d over 4 pi, 2 pi? No, I forget. Remember, this is wrong. D over, D over, where is it? 8 pi, okay. Yeah, 8 pi. Okay. So that's the first order correction. All right, but you can actually go higher orders as well. So if we go higher orders, let me start using an eraser instead of my hand. What's that? That's a good question. I don't actually know. I mean, it's a different mode that can be there, so, but it's going to be very massive, basically. So, the question is, what's the meaning of the higher modes for the harmonic oscillator? So this is the lowest. This is the lowest mode, but it's not clear actually to me. I mean, in a sense, you know, I'm just solving a classical wave equation. I'm using the harmonic oscillator as a guide, basically. So, I mean, these would be some higher modes, and somehow in the, you know, it'll have more radial. It'll have bumps in its distribution. So, all right. So we can actually, since we did a harmonic oscillator, and we threw out this term. Now we can bring back this term, and basically what we're doing is now we're considering a perturbed harmonic oscillator. Okay, and so in this case then you have a sort of a contribution where you have a correction to the Hamiltonian, this delta H, is equal to minus a half times 1 over r to the d minus 1 times d to the dr to the r to the d plus 1, ddr, acting on my chi. And now you can just do first order and second order perturbation theory. So you can open up your favorite quantum mechanics book like Griffiths or something like that. And what you find then, if we assume that our constant is minus 2 over alpha prime plus some, I'm going to make some ansatz as to what this correction is going to look like. Okay, so this is an ansatz. Then what you find then is that the dH, okay, is equal to 1 over 2 pi times the square root of 2 alpha prime plus d over 8 pi plus, we can go to 2 orders here, d plus 1 plus 8 times this delta c term here. Okay, 16 square root divided by 2 pi times alpha prime. Okay, and times d plus 2 times 4d minus 1. Okay, this is just algebra basically to get this. 256 over pi times alpha prime plus, okay, higher order corrections like that. So that basically just comes from doing second order perturbation theory on our harmonic oscillator with this correction to the Hamiltonian, and assuming that I have some correction to the 0-point energy that you get that shifts the mass squared when you basically twist around the thermal time direction. All right, so I should say, where did this ansatz come from? Well, this ansatz came from so it turns out 20 years ago, around the time of BMN, people were studying the plane wave limit, and one of the things they did was they computed the Hagedorn temperature for type 2 string theory in plane waves. Not only that, they did this not just for 2B, but for 2A. Okay, and so even before ABGM was around, okay, they computed this, and they were able to compute it exactly. Okay, and so it was known then. You can look at the results for the plane wave case for the Hagedorn temperature, and you could see that the correction that you would get would correspond to a term that's proportional to beta squared. Okay, so we took that as an ansatz in our equations. Okay, so, and not only that, you can see that what you find is basically using this, that this delta C is going to come with a factor of log of 2. Okay, so doing that, then we were then plugged in, we did all of this quantum spectral curve machinery to basically crank out our results to basically find these terms, both for n equals 4, but also for ABJM. Okay, so we have 2 examples, so we can generalize this to NED. So we did that for that, and basically the result is that delta C, this delta C, is equal to minus d times the log of 2. Okay, we were looking for a log of 2 factor because of the plane wave result, and we found that using QSC, and I should also say I left out a very important names. So this was using a technique by Harmark and Wilhelm. We basically just used their machinery and cranked it up so that we got more accurate results for this term and this term. So that we could actually sort of verify that this was the case. Okay, so they did it for n equal 4, we did it for n equal 4, but then also for ABJM. Okay, and in both cases then it follows this this way. Okay, so, but since then, so you might ask, where does that come from? Why do we get that? And there was a very nice paper by Troels Harmark, which I'd like to tell you about. And about how you can get this result. So let me say how you get that. So when I wrote down this mass formula, which I might have just erased, oh no, it's over here. Okay, so I have this term, okay, and then I have the C, and the C has this part here. Okay, but Troels observed that when we write down this mass formula as it stands right there, it's not actually in a obvious, manifestly covariant form. So in order, but we'd expect it to be in some sort of covariant form. So in order to do that, what I'm going to do is introduce a time-like killing vector. Okay, I'll call this V mu, and we'll have that along the time direction that this is basically equal to beta. Okay, So if I write things like this, then I can write my mass formula as follows. So my mass squared term I can write is equal to I can write it basically in the following form. I can write it as g mu nu times v mu v nu, okay, divided by 2 pi alpha prime. Okay, that should be squared. All right, and so write it like that. So that would you get that term minus a 2 over alpha prime. Okay, and if we were in flat space, this would be the end of the story, because in flat space, then this would basically G00 is basically 1. Okay, and that would be the flat space result. Okay, but but in curve space, okay, this would be a little different. And so the way I've written this term over here doesn't quite fit this. So what I want to do is I want to add another term. I'll call this plus gamma times v mu v nu, okay, so that I get something that will be of order beta squared. So I'm trying to reproduce this term here, okay. But it should be something that's not going to contribute to the flat space term. Okay, so, well, the only thing it can be, you want it to be symmetric in mu and nu, the only thing it can be is r mu nu. Okay, so you get some term that's proportional to r mu nu. In flat space, r mu nu is 0. In curved space, it's not. Okay, but now this should be true not just for ADS, okay, but it should also be true for the plane wave. Okay, and so in the plane wave case, you have that, so ds, let me write down what this metric is. So it's minus some f squared times yi squared times dx plus plus dyi squared. Okay, and in that case, the only non-trivial contribution is r plus plus, which is equal to 8f squared. Okay, so and if we then compactify the time direction, then v plus plus is basically equal to beta squared over 2. Okay, you plug that in to what you know about the Hagedorn temperature then, or the mass squared term for that, and that basically then gives you that this gamma that I wrote down here, that gamma is equal to minus 2 times the log of 2, okay, times divided by 2 pi squared over alpha prime. And so then you get this. But the thing is, now you can use this r mu nu in ADS. And so in ADS, you have that you would have R00, okay, and this is equal to basically this is equal to d times 1 plus r squared. And if I ignore this r squared for now, that gives me my factor of d, which will exactly give me the factor of d here. So it's a beautiful argument about why that's true, why that works. Okay, but the one thing, though, is that now for the next term, this r squared term that I just dropped would actually contribute to this term over here. Okay, so you got to get rid of it, and that means you have to introduce some extra term inside, which actually won't affect the plane wave, because the plane wave, this works for the plane wave. And the term you can introduce is you can basically, what you can do is you can add an extra kinetic term to cancel that. And so the extra kinetic term that you'd add you can add would look like if you could add a minus 2 times the log of 2 times an R mu nu times a d nu, d mu, d nu acting on chi. So this would be an extra term that you would add. And so for the plane wave, you're again assuming chi only has R dependence. For the plane wave, okay, I have too many R's here, but R is equal to 0 for the plane wave. Okay, but it's equal to, but it's not equal to for. It's basically it's equal to, well, it's basically of order d for whatever for ADS. Okay, so anyways, it will contribute a term that will annihilate then this extra term that would have contributed to this guy. Okay, which doesn't appear to be there from the QSC. Okay, now why this term here, though, is here, we don't know, because unfortunately you can't fix it by looking at the plane wave because it's 0. In some sense, it would be better if it wasn't, if it did contribute to the plane wave, but it doesn't. So it's a mystery, you know, how you can generate these terms, how this term would show up, say, from looking from the string world sheet. But let me leave it at that. Okay, so I have 15 minutes, 10 minutes? 10 minutes. Yeah, right, okay. All right, so let me say a little bit more about what Hagedorn means. Let me... All right, so let me suppose I have n equals 4 super Yang-Mills, okay, at 0 coupling, at lambda is equal to 0. Okay, so, and I'm assuming that I put this on S3, okay, and it turns out that this also has a Hagedorn temperature, so which sounds a little strange because it's a non-interacting gauge theory. Okay, but you can do the same sort of things, and this was done by Sundborg a long time ago. And basically what you have is you want to consider all the single trace operators. Okay, where these phi's, these are either the 6 scalars, let's call them phi I like that. So this is a capital phi, this is a small phi. We have the fermions, which either are in the fundamental or the anti-fundamental of the SU4R symmetry, or you have field strengths, okay, or their derivatives, and their derivatives acting on these things. Their covariant derivatives acting on this. So basically then what you want to do is you end up with a counting problem, and if we define a variable y is equal to e to the minus 1 over 2 times the Hagedorn temperature, like the temperature T, sorry, not Hagedorn temperature, then you can find that basically the partition function will be equal to a sum L equals 2 to infinity of 1 over L times some function of y times to the nth power, where this function of y basically is basically counting all the different types of fields you can have here. And so it turns out this function is equal to 2y squared times 3 minus y, okay, divided by 1 minus y cubed. Okay. Now this isn't exactly the answer, but it turns out that when you're considering the case where you have very long operators, L, by the way, is counting the number here of operators in the number of fields in the chain here. When this gets very big, this is good enough. You don't need to worry about Euler-Toshan functions and things like that, which is in the original thing. So anyways, you can see then that that this is basically logarithmically divergent. So this is minus the log times 1 minus zeta of y. Okay, and so this is, and so this will diverge if zeta of y is equal to 1. And if you set this equal to 1, then this will give you the value for the temperature at which when you hit a phase transition, basically. Okay, so now what happens, though, is there's another interesting thing that happens at this same temperature, where this zeta of y is equal to 1. So, and y just turns out to be equal to like 2 minus the square root of 3. You can check. What happens, though, is another thing happens, and this is what's known as deconfinement. Okay, and so again, n equals 4 can have a deconfining phase transition. And that sounds kind of strange because, first of all, we're talking about zero coupling. Second of all, n equals 4 is not a confining theory. Okay, but really the way you should think about it is we're putting the theory on S3. Okay, and on S3, what we should be only looking at are the gauge invariant states. Okay, and so when you impose this condition on only having gauge invariant states, if the temperature is low enough, then basically you're in what's known as a confining region. Okay, but as you raise the temperature, there'll be a phase transition and you go to this deconfined region. And then basically what happens is the entropy goes from being of order 1 to being of order n squared. Okay, so this partition function, let me call it z1 for this case then, actually z for this case, is equal to, this was computed again by Sundberg, that this is basically e to the sum of n equals 1 to infinity of 1 over n times the contribution of these zetas to y to the n, where this is the contribution from the bosonic fields, and minus 1 to the n times the contribution for the fermionic fields, y to the n, times the trace of u times the trace of u dagger, actually to the nth power, like that. Okay? So you can actually see then that that over here, that if n is equal to 1, then basically you get this sort of behavior like this, and you can see basically that you're going to have a same sort of phase transition at the same point as you did over here where the Hagedorn temperature is the Hagedorn temperature. Okay, well, I don't have enough time to go into it, but if you check, you can actually see that you have this phase transition. Okay, so roughly speaking then, what happens then is that for n equals 1, okay, then this zeta by plus zeta fy, okay, this is equal to the zeta y. Okay, when this is equal to 1, you have this deconfining transition. Okay, and this happens at the same temperature. So the temperature for deconfinement is equal to the temperature for Hagedorn. All right, so I don't have a lot of time, so I'm just going to finish by drawing some graphs and making some comments. Okay, so basically what's happening is that if I draw a graph of the free energy versus U, where this is, say, the expectation value of these U values up here. So these are in the in these states here. I mean, in these from these gauge variables here. What you find is that so for what happens then is that for lambda equals, so for at t, well, let me draw it like this. So for T less than TH, the free energy sort of looks like this in this case. T equals TH, it looks like this. Okay. And T greater than TH, it looks like that. Okay, so basically what happens then is you're going to have a weakly first order phase transition when you cross the this critical temperature, which is the Hagedorn temperature, which also turns out to be the deconfinement temperature at zero coupling. Okay, so let's suppose now that lambda is greater than 0. And what we expect is the following, is that, so now it turns out, in this case, the deconfining temperature is less than the Hagedorn temperature. And basically what's going to happen is that if you look at this thing, this is quadratic in the U's. As you turn on couplings, you're going to turn on things that are cubic and quartic and things like that. And the effect of that is to basically then make this Hagedorn temperature less than TH. Because sort of what's going to happen then is if I draw this free energy like this versus the expectation value, then I get something that looks, okay, so if T is greater than T, if T is less than TD, it still goes like this. Okay, if T is equal to the deconfinement temperature, it's basically going to go like this. So this is T equals TD. Okay, and if T is greater than TD, okay, it's going to look like this. Well, actually, not like that. It's going to go up, but then it's going to go down like that. Okay, so this is T greater than TD, but less than the Hagedorn temperature. Okay, so from this you can see that you're going to have a first order phase transition. Okay, and this is basically determined by the sign that you get when you compute this. You can use perturbation theory to find corrections to this term. Okay, and what's important is what's the sign of the quartic term. And so this was actually done for pure SUN. And in this case, the sign was negative. Okay, so there you find then that you end up, so since the sign is negative, the quartic term will pull this thing down, and you end up over here. So what Hagedorn is telling you basically then is that it's basically giving you the curvature right at the origin. Okay, and so you can have a metastable state, and in this state you're in the confined region. Okay, but when you're, but then if you're over here, you're in the deconfined region. And then if T is if T is greater than TH, then there's no metastable state. Okay, so that's what Hagedorn is telling you. Okay, so let me just say one thing about this. So this calculation was done for pure SUN. This was done by Araroni and Menwala, Marsano, Van Ramstonk, and I'm forgetting one name. But in 2005, and they said that they were going to have the results for n equal 4 shortly. Okay, but 2005, as best as I know, it has still not come out. But I'm always sort of hopeful that this calculation can be done using integrability. I don't know how to do it using integrability, but I kind of think that it should be. Now, let me finish by just saying what I would expect. I would expect it to be negative. And the reason for that is we actually know at very strong coupling that actually if T is greater than a temperature of order 1, where we're using units where the radius of our S3 is of order 1, then the deconfinement transition takes place at order 1. And this is because this is where the Hawking-Page transition takes place in the string theory, where where thermal ADS is no longer the configuration with the lowest entropy, lowest action. Okay, it's actually this ADS black hole. And so there you expect this transition, and you expect it to be first order. So I would like to go beyond Hagedorn and say something about deconfinement using integrability. And I'm hoping some of you young, adventurous people in this audience will do this. So, okay. Well, thank you for your patience.
Thank you.
So you had an expansion at strong coupling for the
Yes.
Hagedorn temperature.
Yes.
I was wondering at what order you think the theory-specific terms would kick in. So to match the free, gauge theory or free n equals to 4 answer, which is constant at lambda equals to 0. I was wondering.
I'm not sure I understand the question. I mean,
So you had an expansion for the Hagedorn temperature
Yes.
at strong coupling,
Yes.
but then at weak coupling,
Oh,
you
okay.
need that to agree.
Yeah. Okay, we did this.
Right.
Okay, we went from zero coupling to strong coupling. Okay, numerically. Well, also we can do the expansion at weak coupling. You can also do the expansion in orders, perturbatively, and you find analytic expressions in front. So so it was first done. The first correction in n equals 4 at weak coupling was done by Spradlin and Volovich in 2004. Okay, and then I think a 2-loop calculation was done. But then Harmark and I've erased them, but then they went up to 7 loops. Okay, and they know the Hagedorn from that. But then what they did and what we did is we can start at weak coupling and we end up, and you can get this result that you get for this weak coupling result, and you go up and you match onto well, it's now erased, but onto the expansion I had before.
Do you think
and you do that in an ABJAM as well.
Is it possible to see, like, to know what order in this alpha prime going to 0 expansion you expect to see some theory dependent terms?
Oh, you mean more than just this D dependence?
That's right. Yeah.
Well, okay, the D, I expect the next order that then it might become more dependent on the theory because basically you're going to have corrections to this 0-point shift, and I imagine that will depend on it. I don't know for certain. So we've been trying, we actually know numerically, we know the next couple terms in the expansion, but we don't know them well enough to basically say for certain what they are. We had some guesses and they didn't seem to work that well as we improved our accuracy, but we're counting on their new quantum, their new results to actually do better at this. Because we have the same problem that at strong coupling that you had for computing the dimensions of operators. I mean, really what Hagedorn is telling you is the density of states as you go to large energies, right? So in a sense, they're looking at the individual energies in here, but we're basically looking at the density of states.
Yeah, thank you.
Can you switch on chemical potentials, let's say counter?
Yeah, we're trying. Yeah, we can. And in fact, so ABJAM, not ABJAM. On the plane wave, they did turn on chemical potentials. And so they know what those will be. And we actually use but we're trying to do it, but it's a lot more, it's more unstable numerically. So far we haven't managed to do it.
And how the phase diagram looks if you say plot temperature as a function of chemical potential?
Let's see. I don't know at the top of my head. I have to think about it.
Okay, as I said, we have lots of time. Okay,
Right,
very last one.
He's the founder of the conference. You have to let him.
Very good.
Thank you. Thanks for a very nice talk. Could you in principle do such a calculation on more complicated backgrounds, like for example Lunin, Maldacena, some specific simplest case, to compute the Hagedorn temperature?
I'm not going to say no, but I'm not sure exactly how I would start. I don't know. I mean, as far as I know, you guys have never done anything on backgrounds, right? quantum. Oh, okay, beta. Yeah, I guess it's beta deformation. Yeah, and principally, then you can do it.
It's the same calculation, just a little bit more complicated.
Yeah, it's more complicated. But it could be that the numerics will become much more unstable as well, just like turning on chemical potentials, you know, deforming it. I'm not sure though.
Okay,
Oops, sorry.
thank you.
Okay, let's thank Joe. And we have now the talk by Istvan.
Okay. Can you hear me? It works. Nice. Okay. And